Okay. Right. Okay. So yesterday, we completed up to normal shift. That is correct? Normal shift. Okay. Now there's one more thing. There's two more things that we need to finish over here. So in this normal refraction, that is the refraction by prism. Next, refraction by lenses. Got it? Okay. Now the second, you see, give the heading. There's a refraction by prism. Refraction by prism. Refraction by prism. We need business. Refraction by prism. Okay. How does the refraction take place in the case of prism? This is what we have to think of now. This is what we have to think of now. How does the refraction take place through a prism? So first of all, you need to have some idea about the prism because so practical examinations were not conducted. Therefore, so some of you might not hear, so you will see. Okay, so might not have it, so have the might not have so have seen. So did you see the prism? How it is? Okay, so prism, the actual shape of the prism, if you want to see, the actual shape of the prism will be like this. Look at this here, you see. So it is a triangular shape structure like this, which is made up of glass like this. Right? So this is the other face over here like this. So this is the actual shape of the prism, 3D view. The 3D view of prism can be shown like this. Right? So this is complete solid. And I don't think that always prisms are made up of solids. Okay, so there will be some there's a prisms in which okay, some crystals may be present over here. So that is called crystalline prism. And even if you take any plastic material, okay, or there's a fiber or anything, so even plastic prisms are also available. And whatever it may be, that so that has to be transparent. Whatever it may be, that has to be transparent ultimately. That has to be transparent ultimately. But so for this entire prism, so this surface becomes the first refracting surface, and so this surface becomes the second refracting surface. If at all you take any object before this prism, let this be the object over here. Okay, now the image of this object will get formed. In what way? So for that, the light ray passes in this direction. Right? So you will be drawing one perpendicular over here, which is called label. As the light ray enters from air into the glass, which is from rarer medium to the denser medium, what happens? The light ray will undergo refraction towards the normal like this. Okay, now this is the second surface. On the second surface, second refraction begins. During the second refraction, the light ray will be passing from glass into the air, denser in so to rarer. Okay, when the light ray passes from denser to rarer, what happens? The light ray will be moving away from the normal. Away from the normal. That means the light ray will be just moving away like this. But if I show like this three-dimensionally, the study becomes very complicated. That's why this complete 3D view we will be discussing as a 2D view. Right? So in what way? Look at this. This complete first refracting surface will be taken as one line, and the complete second refracting surface has to be taken as one more line. Usually, there will be some angle between these two lines, which we call as the angle of prism. So usually, angle of prism is A, B represents. This is one refracting surface. This is one more refracting surface, and this bottom one, this becomes the base of the prism. This becomes the base of the prism, right? Now, this becomes one refracting surface over here. This becomes one more refracting surface over here, right? Now, so there is a base present over here like this, right? So whatever the complete this refracting surface I have shown as a line, this is the first refracting surface. And what about the second refracting surface that we have in this 3D view? The complete second refracting surface I have shown as a line over here like this. There will be some angle between the two surfaces. That is this, which is known as the angle of prism. That is known as the angle of prism. This is base of the prism. This is the base of the prism. Got it? Base of the prism. Right. Now I will be taking one point object over here like this. Now, how does the refraction take place? The light ray will be just passing over here like this. This is the way how the light ray passes. This is A. and this is glass. Again, this is air. When the light ray enters into the glass, what happens? Imagine one perpendicular which you are calling as normal. As the light ray passes from air to glass, the light ray undergoes refraction and the light ray will be just passing over here like this. This is the way how the light ray passes. This is the way how the light ray passes. Now the second refraction begins from the second surface. Now to estimate the position of the second refracted ray, we need one normal. The normal is like this, perpendicular. The normal is like this, perpendicular. Got it? This is the normal, that is N, O, N dash, you say, and this is the normal which is M, this is O dash, and this is M dash, you say. These two normals are intersecting at a particular point which is X over here. As the light ray passes from glass to air, which is from denser to rarer, what happens? The light ray will be just moving away from the normal. The light ray will be just moving away from the normal over here. Now you need to write angles of incidence and angles of refraction and remaining rays. And here, the angle between the incident ray to the normal, this becomes the angle of incidence, that is I. The angle of refraction will be where? This is angle of refraction, which is R. But one more angle we come across over here. So this is R1, we say. One more angle we come across over here. So I1, you say. Got it? So when this is R1, even this thing also becomes R1. That's R2. Of course, both things may be equal, may not be equal. That we can't say. That depends upon the angle of incidence and prism angle. Based on these two things, whether these two angles R1 and R2 equal or not equal depends. Right? Now this is the light ray which is obtained after completing all refractions. Therefore, that particular light ray is known as an emergent ray. This is called emergent ray. This is called emergent ray. This is called emergent ray. Emergent ray. Right? So this emergent ray is making some angle from the normal. So this is called angle of emergence. Usually, the angle of emergence is also shown as E, but here I1 I have shown already. So this becomes I2. This becomes I2. Why I1, I2 I have shown? In the sense there is a reason behind it. What is the reason behind this I1, I2? We will be establishing some equations in terms of I1, I2, R1, R2 like that. That's why I have shown I1 and I2, R1 and R2 like that. But it is okay. Now this is a prism angle, that is A. Right? Now, so if at all this light ray is extended, what is that light ray? This light ray is nothing but incident ray. This must be the actual propagation of the light ray. If the observer sees from this side, this is observer's position. For this observer, this light ray seems to be coming from an imaginary point over here. Let this point be Y. Let that point be Y. Let that point be Y. Got it? Okay. Now, from the usual propagation, what happens? This light ray is getting deviated over some angle. This is known as the angle of deviation, delta. That is called the angle of delta. So deviation. This is called the angle of deviation, we call. This is called the angle of deviation. The angle of deviation. Usually, in the case of prism, we come across one more technical word, which is the angle of minimum deviation. The angle of minimum deviation, sometimes we come across. The angle of minimum deviation. But remember, every time the prism may not be in the position of the angle of minimum deviation. Okay, so if at all you want to have the angle of minimum deviation, there must be some condition. When the prism meets those conditions, then the angle, the complete prism will come in the position, the angle of minimum deviation. And what is that? The angle of minimum deviation means what? What is the concept of the angle of minimum deviation? Look at this. This is the angle of incidence. You just try to visualize how the position of these two light rays will be changing. When this incident ray is shifted downwards, automatically this emergent ray will be moving upward. Am I correct? Yes or no? So when the emergent ray moves upward, what do you say about angle of deviation? It will be decreasing. You are moving this incident ray downwards. Means what do you say about this angle of incidence I1 increasing? That means what do you say here? Yes, the angle of incidence increases, the angle of deviation decreases. But this type of decrease in the angle of deviation never takes place continuously. Yes, this angle of incidence is increased, the angle of deviation will be decreasing. Okay, but don't think that this type of decrease in the angle of deviation goes on taking place continuously. Okay, so yes, this angle of incidence is increased, it keeps on decreasing. In that decreasing aspect, it will be reaching to a minimum value. After reaching the minimum value, even if you increase this angle of incidence, it won't further decrease. It will start increasing. It will start increasing. Once again, I repeat. Here, yes, this angle of incidence is increased gradually. The angle of deviation will keep on decreasing. The angle of deviation will be reaching to a minimum value. After reaching the minimum value, even if you increase this angle of incidence, it will start increasing. Whatever the minimum value to which this angle of deviation is reaching, that particular angle is known as the angle of minimum deviation. That particular angle can be taken as the angle of minimum deviation. Are you clear with this point? Are you clear with this point? Okay. Now, at angle of minimum deviation, what happens? That angle of minimum deviation. Remember, that angle of minimum deviation. That angle of minimum deviation. This angle of minimum deviation we will be representing as delta m, we say. Yet delta m, we see practically that I1 will be equal to I2. When I1 and I2 become equal, ultimately R1 and R2 will be equal. Got it? So R1 is also equal to R2. How can we say this? Graphically we can show. And if you draw a graph between the angle of incidence and the angle of minimum deviation, and you will be getting a kind of graph. So what is that? Look at this. This is a graphical representation. And along the x-axis, I will be taking the angle of incidence values. Along the y-axis, I will be taking the angle of deviation values. When the angle of incidence is very small, the angle of deviation will be high. As the angle of incidence increases, the angle of deviation will be decreasing. The angle of deviation reaches the minimum value. Remember, this angle of deviation will not become zero. If at all this angle of deviation becomes zero, this curve would have come to the x-axis. So this never comes to x-axis. That means that this angle of deviation, minimum deviation, will never become zero. But after reaching the minimum value, still you are increasing the angle of incidence. Then, so the angle of deviation will start increasing like this. The angle of deviation will start increasing like this. And whatever this lowermost point you are getting, this lowermost point can be taken as the angle of minimum deviation, which is delta m. Right? Now, if at all you take any line parallel to x-axis, okay, so here, this is one point of intersection, this becomes one more point of intersection. This is the x-axis along which you have taken the angles of incidence. From this point, if you draw one perpendicular, so this becomes I1. And from this point, if you draw one more perpendicular, this becomes I2. Now, there is a gap between this I1 and I2. Yet this stage, that means yet this angle of deviation. Okay, so this is delta 1 you take. Yet delta 1, I1, I2, both things are quite different, so far away. Now, I am moving down. Means I am moving towards the angle of minimum deviation. If I do that, look at this, one more line I have taken over here. I am just moving towards the angle of minimum deviation position. Then what happens? This becomes one more point of intersection. This becomes another point of intersection. From these 2 points of intersections, you draw 1 or 2 perpendiculars over here. Now this becomes I1 and this becomes I2. Even then, I1, I2 are separated apart. There will be some distance between I1 and I2. But this distance is lesser than the previous distance. Am I correct? Okay, that means by means of these 2 observations, what's our conclusion? As you approach the angle of minimum deviation, the distance between I1 and I2 is decreasing. And if you take one more line over here, which is very close to this angle of minimum deviation, further you are moving down like this. Further, you are moving down like this. This becomes one point of intersection. This becomes one more point of intersection. Now, this becomes one perpendicular. This becomes one more perpendicular. Now, this is I1 and this is I2. What's happening over here? What's happening over here? As you move closer and closer to the angle of minimum deviation, the distance between I1 and I2 will be decreasing. The distance between I1 and I2 will be decreasing. Okay, if you take the point exactly, that is the angle of minimum deviation. Exactly the angle of minimum deviation. Then what happens if there is only one perpendicular, you will be getting. That means this I1 and I2, both the things will be that itself. So I1 and I2, both the things are coinciding over here at this point. So this point is nothing but I1 is equal to I2. Now, did you understand how I1 and I2 are equal? One thing we have to conclude. What is that? When the prism is in the angle of minimum deviation position, both the angles of incidence will be equal. Okay, so that will be equal to I, you say. This is I, you say. Okay, so from this figure, when I1, I2 are equal, so ultimately R1, R2 also will be equal. When R1 is equal to R2, so that I say yes, R. One arbitrary value I will be taking. One arbitrary value I will be taking. Got it? So I1, I2 and R1, R2 like that. Now equations we need to establish. And how to establish the equation? Look at this. This is A, this is O, this is O dash, this is X. Now look at the figure A, O, X, O dash. And what do you say about this? A, O, X, O dash. That forms the quadrilateral. In a quadrilateral, the sum of 2 opposite sides will be 180 degrees. Of course, sum of 2 opposite sides is equal to 180 degrees means that happens in the case of cyclic quadrilateral, but we can prove that this is a cyclic quadrilateral. A, O, X, and O dash. This forms a cyclic quadrilateral. Therefore, in this particular case, the sum of 2 opposite angles of vertices, that is A plus angle OX O dash, OX O dash, that will be equal to 180 degrees. A plus angle OX O dash is equal to 180 degrees. 180 degrees. Got it? Now, angle OX O dash, angle OX O dash is equal to 180 minus A. 180 minus A. Understood? 180 minus A. Now look at this triangle. Triangle O dash X. Triangle O dash X you take. In this triangle, I am taking triangle O dash X. O dash X. In this triangle, R1, which is one of the angles of vertices, R2, that is the angle of the second vertex, plus the angle OX O dash. OX O dash. That is equal to 180 degrees. The angle sum property of a triangle. The angle sum property of a triangle. Got it? R1, R2 plus angle OX O dash is equal to 180 degrees. The angle OX O dash and we have written over there. 180 minus A. So this becomes R1, R2 plus 180 minus A is equal to 180. These two things get cancelled out. Therefore, R1 plus R2 is equal to A plus A, that's all. R1 plus R2 is equal to A. So this is the equation 1 over here. Why I have written this equation in the sense that don't think that at last we will be getting one equation. That equation, what is that equation? What is that equation? The refractive index of this prism is equal to sine A plus delta M by 2 by sine A by 2. That equation we will be getting. That equation we will be getting. So don't think that only that equation we will be using while solving the problems. There will be some problems in which R1 plus R2 is equal to A. This result we will be using. This result we will be using. So I have written this equation. R1 plus R2 is equal to A. That is one equation. Now look at the other triangle. OY O dash. OY O dash. Now look at this triangle. Triangle OY O dash I have taken. In this triangle, so this angle, what is that? The angle O dash OY means this angle plus the second angle, which is O dash Y. O dash Y means this angle plus the third angle of the triangle OY O dash. This is OY O dash. That should also be equal to 180 degrees. This angle is what? Can you tell? Look at this. This is a straight line. This is a straight line. This becomes I1. Then the whole thing becomes I1. Am I correct? When whole thing becomes I1, so this will be what? I1 minus R1. So whatever the first angle I mentioned over here, that is the angle O dash OY. Its value is I1 minus R1. I1 minus R1 plus. And the second, look at this. This is one triangle, this is a straight line. This becomes one more straight line. So when this is I2, this complete angle becomes I2. But from here to here, R2. Then what do you say about this angle? I2 minus R2. So this becomes I2 minus R2 plus. And what about this angle over here? 180 minus delta. This becomes 180 minus delta. That is equal to 180. 180 minus delta is equal to delta. So these two things, so 180 will get cancelled out. Right? I1 plus I2. Right? Minus R1 plus R2 is equal to delta. Right? R1 plus R2 is equal to how much? A. If you write this one here, so what will you get now? I1 plus I2 is equal to A plus delta. This is one more equation that you will be using while solving the problems. That is another equation that you will be using while solving the problems. I1 plus I2 is equal to A plus delta. A plus delta. Another equation that is. Okay, so far, one thing we didn't consider yet. What is that? The angle of minimum deviation position we did not keep in mind so far. Now I will be assuming that the complete prism is in the angle of minimum deviation position. When the prism is in the angle of minimum deviation position, what do you say? I1 is equal to I2, R1 is equal to R2. I1 is equal to I2 is equal to I. You say I1, I plus I, 2I. Okay, so 2I is equal to A plus delta M we can write. Because now I have assumed that the prism is in the angle of minimum deviation position. The angle of minimum deviation position. Therefore, 2I is equal to A plus delta M. Therefore, I is equal to how much? This is A plus delta M by 2. This is the angle of incidence now. Okay? Now, R1 plus R2 is equal to A. When both things are equal, R1 is equal to R and R2 is equal to R. R plus R is equal to A. Therefore, R is equal to A by 2. So this is what? One more equation we will be using. Whatever the equations I have written over here, all these equations we will be using while solving the problem. So I am telling you, don't forget. Now, the refractive index of this prism we need to write. The refractive index of this prism, which is mu by Snell's law, sin I by sin R. This is Snell's law, refractive index of glass prism. I value we have here, that is sin A plus delta m by 2. This becomes the I value divided by sin A by 2. This is R value. Sin A plus delta m by 2 by sin A by 2. That is R value. That is R value. Ultimately, mu is equal to sin A plus delta m by 2 by sin A by 2. This becomes the refractive index of the glass prism. The refractive index of glass prism. Please make a note of it. Make it fast. Understand? Now, in this case, we will come across some special cases. Yes, now the special case we need to take up. So what is that special case? Sometimes whatever the prisms that you are going to handle, those prisms are of thin prisms. Thin prisms, very, very thin prisms. Correct? Thin prism in the sense at what range the prism angle do you have to take? At what range the prism angle has to be taken? This is what we have to keep in mind. This is what we have to keep in mind. At what angle, till what angle we need to take the prism angle. This is what we have to think of. Usually, up to 4 degrees to 5 degrees we can take. Up to 4 degrees and 5 degrees. So prism angle. Okay, so this can be considered as a thin prism. Okay, right? Okay, so for thin prisms, look at this. This refractive index mu is equal to sin A plus delta m by 2 by sin A by 2. This is what the equation that we obtained just now. A sin delta m by 2 by sin A by 2. Got it? So for thin prism, this A plus delta m by 2 is very small. This is very, very small. When this is very, very small, this sin A plus delta m by 2 can approximately be taken as A plus delta m by 2. There will be no much variation. In what way? Of all the angles, 0 degrees is the smallest. Sin 0 is equal to 0. Got it? So like that, sin 30 is equal to 30. Are we taking? No, that is wrong. Sin 45 is equal to 45. Are you taking? No, that is wrong. Okay, sin 0 is equal to 0. So this type of thing happens only with 0. Means when the angle is too small. Okay, so but this type of thing, will it hold good for cosine function? Is cos 0 is equal to 0? No. Cos 0 is equal to 1. So this type of assumption, this type of approximation can be taken only for sine. And one more thing we come across, tan you take. Even tan 0 is equal to 0. Even for tan also, it is applicable. Correct? That's why for smaller angles, sine of that angle can almost be taken as tan of that angle. That's what we took up in yesterday's discussion, that is normal shift. In normal shift, we took up that. Normal shift. Got it? Okay, sine theta is equal to tan theta. Approximately we can take when theta is too small. And in this way, even this A, prism angle, is also very small. When the prism angle is very small, then what do you say? Even this sine A by 2 can approximately be taken as A by 2. Approximately be taken as A by 2. Got it? Now, by keeping these values in the equation of this, by keeping these values in this equation, so what do you say? The refractive index is equal to, in the place of sine A plus delta m by 2, I will be just writing A plus delta m by 2. This is what I am writing over here. Divided by, in the place of sine A by 2, I am just writing over here, that is A by 2. Now, if you go for cancellations, this A will come here. So this becomes mu A is equal to A plus delta m. Mu A is equal to A plus delta m. Therefore, so delta m in this particular case is equal to A into mu minus 1. So this is what the angle of minimum deviation for a thin prism. This is the angle of minimum deviation for a thin prism. Delta m is equal to A into mu minus 1. Delta m is equal to A into mu minus 1. This is another important equation that we have to keep in mind while solving the problems with this. Okay? Understood? This is how refraction takes place in the case of glass prism. Glass prism. Now, refraction, how it takes place in the case of lens. Refraction by a lens. Refraction by a lens. Refraction by a lens. Right? Now, what do you mean by lens? This is what we have to think of now. Refraction by, give the heading. Refraction by a lens. Refraction by a lens. Refraction by a lens. Right? Now look at this refraction by a lens. What do you mean by lens? This is what we have to think of now first. What do you mean by lens? A lens is nothing but, look at this, here you see, there will be one solid sphere that we will take. And one more sphere we have to take of equal dimensions. Now, these two spheres have to overlap. When these two spheres overlap with each other, there will be some intersectional portion. What about the intersectional portion that we come across? That is nothing but lens. In what way? Look at this. Here you see, this is one more sphere we will take. This is one more sphere we will take. Got it? Now, this becomes the intersectional portion. This becomes the intersectional portion. Intersectional portion. Got it? Okay, so this intersectional portion, if you want to remove, then you will be getting this type of shape over here like this. This is the shape that you are going to obtain. Right? And if you see this from this side, it becomes a convex surface. If you see, okay, from this surface, okay, so this becomes convex. This is convex, double convex. Or this is called biconvex lens. This is called biconvex lens. Got it? So this is biconvex. So this is convex. This is convex. Right? And if at all, you take the refraction, how it passes, how it takes place. The propagation of light ray has to be taken from left to right. Universal sign convention. Universal sign convention. Always the propagation of light ray has to be taken from left to right. In taking like that, left to right you are taking. What is the surface which is touched by the light rays? This is the surface which is touched. So this is called primary surface. That is called primary surface. Now the second surface will be the secondary surface. Primary surface and secondary surface. Primary surface and secondary surface. Right? Okay. Now if at all you extend this, then you will be getting one sphere. To that sphere, there will be one center. This is the geometric center for this primary surface. Therefore, this is known as a primary center of curvature. Last bench. What's happening? Okay, see here, this is a center for this curvature. So this is what curvature? Primary curvature. So this becomes a primary center of curvature. Primary center of curvature. And in the same way, this is the secondary surface. And if at all you extend this thing, again you will be getting the sphere, which is nothing but this. Even for the sphere, there will be some center, which is called geometric center. This becomes a geometric center, you see. This becomes the secondary center of curvature, because this is the center for the secondary surface. Don't have any confusion with the primary center of curvature, secondary center of curvature, like that. But now, this is the primary surface. Now, the midpoint of the surface, if you take, this becomes the pole, primary pole. That is a primary pole. Correct? Now, the primary pole and the primary center of curvature, if you join, you will be getting primary radius of curvature, R1. Correct? Now, if at all you extend this, okay, so there will be some center for this secondary curvature, that is P2 over here. This is a secondary pole. Now, the secondary pole to C2, if at all you join, you will be getting one more radius, which is radius, secondary radius of curvature. That is nothing but secondary radius of curvature. Secondary radius of curvature. But if at all you take one light ray which is passing like this will be having one focus over here. The focus will be F1, which is a primary focus. And similar focus can be had even here. This is a secondary focus, which is F2. Yet once I am explaining the shape of convex lens and all the terms related with that. Both things are happening over here simultaneously. Yet a time. Okay, still some boys are talking in the last bench. If at all you want to talk, all two boys went, they are talking nicely over. You also go. I don't have any objection. Okay, since I am teaching, all boys must be present. No, there is no compulsion. Whosoever wanted to hear, be here. Otherwise, you go and enjoy outside. Right. So this here, by means of this, what did you conclude over here? So for a convex lens, all primary things lie on the right side. All secondary things lie on the left side. This is what we have to keep in mind. All primary ones are on the right side. All secondary ones are on the left side. Okay, now I will be taking up the concave lens. Concave lens, how do we get concave lens? Even here, you will be taking the combination of two leather spheres. Solid spheres we have to take. Got it? Okay, so this becomes one solid sphere, right? And this becomes one more solid sphere over here. But the thing is, overlapping of these two spheres should not be taken. There must be some gap in between the two spheres. And whatever the gap present in between these two spheres, this gap has to be filled by the similar material. And if at all, this is made up of flint glass, same flint glass we need to use to fill this gap. Then this shape you will be getting, so this is called concave lens. Why concave? From here, if at all you look at the surface, that becomes concave. From there, if you look at the surface, that becomes concave. Got it? Concave surface, concave surface. Ultimately, what do you say? This is a double concave lens, or biconcave lens also we say. That is called biconcave lens also we say. Now, similar terms can be explained over here. Now, if at all you place this concave lens in front of light propagation, propagation of light has to be taken always from left to right. Universal sign convention. universal sign convention. In that way, this is the surface which is touched by the light rays. Therefore, this becomes a primary surface. And the surface which is on the other side, this will become secondary surface. This primary surface, secondary surface, this type of terminology is very, very important while implementing the lens maker's formula, all the things. Remember, for this only one thing I am depending on, that is universal sign convention. Universal sign convention says that the propagation of light ray has to be taken always from left to right. In doing so, the surface which is touched by the light rays, that surface becomes a primary surface, and the other surface becomes a secondary surface, and the other surface becomes a secondary surface. Okay, now this is primary surface. I am just here extending like this. When I do that, you will be getting one sphere. That is nothing but this. This sphere will be having some geometric center. Let this be the geometric center, which is C1. What is this? This is a primary center of curvature. This is the center for this curvature. What curvature? Primary curvature. So this is a primary center of curvature. In the same way, if you extend the second surface, you will be getting one more sphere. To that second sphere also there will be one center, which is the geometric center of the second sphere. This is the sphere center for the secondary surface. Therefore, that is known as a secondary center of curvature. For this primary surface, there will be one midpoint which is known as a primary pole. For this secondary pole will be there here. This is P2. That is P2. Got it? P2. Right? Now, C1 and P1 you connect. You will be getting one radius of curvature, which is known as primary radius of curvature. Next, P2 and C2 you would join, then you will be getting one more radius of curvature, which is R2, which is known as a radius, secondary radius of curvature. Usually, these two radii of curvatures, when you join and extend, you will be getting one axis which is known as a principal axis. Even in the case of convex lens, this will become the principal axis over here. Now, you will be sending one light ray, a parallel beam of light ray, parallel beam of light ray you will be sending over here like this. Then what happens? The light rays undergo divergence. Divergence in what way? So from the surface, light ray passes like this. Again, from the surface, light ray passes like this. And at the same time, from the surface, light ray will be passing like this. Again, the light ray will be passing like this. And if at all you extend this final emergent ray, so these two light rays will be just meeting at a particular point. This particular point can be taken as F1. That F1 is nothing but primary focus. You see, even in my drawing, I didn't show F1 at the midpoint of this C1 and P1. By means of this, what can you conclude? This focus does not lie at the midpoint of this radius of curvature. But in the case of mirror, the focus always lies at the midpoint of radius of curvature. But that will not happen in the case of lens. Even by equation also I will show you. Wait for some time. After 2 minutes that will come. But similar focus we will have here also. So that becomes a secondary focus. When there are two surfaces, there will be one plane which will be separating the two surfaces. So that plane can be taken as a central plane. The central plane intersects this principal axis at a particular point which is known as optic center. So that is C. Optic center. C stands for optic center. C1 stands for primary center of curvature. C2 stands for secondary center of curvature. Now, in the case of lenses, all distances are to be measured from the optic center. In the case of mirror, all distances are to be measured from the pole. Remember. In the case of mirror, all distances are to be measured from the pole, whereas in the case of lens, all distances are to be measured from the optic center. So this is something about the lenses. This is something about lenses. Okay, now one more thing that we need to keep in mind in the case of lenses. Have you done this? Come on, please make it fast. Roughly. Freehand diagrams are enough. Right? Hold on. Now, in the case of lens, how convergence takes place and how divergence takes place. So this, with a reason, I will tell how convergence takes place through a convex lens and how divergence takes place through a concave lens. With a reason, you have to understand. Look at this. Refraction through a convex lens. Keep the heading. Refraction through a convex lens. Refraction through a convex lens. Refraction through a convex lens. Look at this. I am taking one convex lens over here like this. Convex lens, somewhat thicker in size, I have drawn to show the refractions clearly. Right? See here, this is principal axis. Right? By sign convention, you need to take the propagation of light ray from left to right, always. You sit separately, boy, behind. Only. Come here. Separate. Okay. Still, if talking is not controlled, I will make this. But your next position will be this. Right? This. Okay. So this is convex lens, and this is the principal axis. This is the principal axis. But okay. So as per the sign convention, universal sign convention, I will be taking the propagation of incident ray from left to right. From left to right, I will be taking the propagation of light ray. Now, the light ray is just passing over here like this. Right? And if it is a plane surface, look at this, there is a plane surface over here. And if at all you take a light ray propagation like this. Right? Now, this is glass, complete glass. This is complete glass. Now, to estimate the position of the refracted ray, what do you have to do? You need one normal. Since it is plane, directly we can draw normal. So this becomes normal. Am I correct? So this becomes 90 degrees. But the type of possibility is not there in the case of this lens because this is curved surface. Curve. But in such cases, what do? We will be taking one point over here to this point, to this curve, through this point, one tangent you need to Draw. This becomes a tangent. Tangent. To that tangent, you need to draw one perpendicular. This becomes a perpendicular. That perpendicular becomes normal. That perpendicular becomes normal. Right? Now, as the light ray passes from air into the glass, rarer medium into the denser medium, then what happens? The refracted ray will be bending towards the normal. Towards the normal in the sense in this way. This must be the propagation of light ray towards the normal. Now the second refraction takes place from the second surface. During that, again, you need one tangent. This becomes a point of incidence. Right? Now you need to draw one tangent over here. Now to this tangent, you need to draw one perpendicular. This becomes the perpendicular over here. That becomes the perpendicular. Now what happens? Light ray is passing from glass into air. When the light ray passes from denser medium to the rarer medium, the refracted ray moves away from the normal, as we know from the previous discussions. Now, away from the normal. This is the normal, away from the normal. Yes. Okay, this is away from the normal. And if you take one more light ray, which is passing here, even this light ray also obeys the same type of refraction. Now, again, this becomes a tangent. This becomes a normal. During the first refraction, the refracted ray will be bending towards the normal. Again, this becomes the point of incidence. This becomes the tangent. This becomes the perpendicular. Away from the perpendicular, which is normal. Like this, the light ray. This is how a convex lens behaves as a converging lens. Why converging? Because after the two refractions get over, whatever the light rays which are coming out of the lens, all these light rays will be coming closer. All these light rays will get focused at a particular point. So that is called a converging point. All the light rays converge each other. Therefore, this is called convergence. This is called convergence. Therefore, a convex lens is a converging lens. And same thing in the case of concave lens, if at all you want to show concave lens, which is a refraction through a concave lens. What happens over here? Like this, same discussion. I will be taking one concave lens over here like this. This is concave lens, right? This is the primary surface 1, and this is the secondary surface 2. In fact, no concave lens will be that much thicker. Wantedly, I have shown to show these two refractions clearly. In fact, the thickness of the lenses will be very, very small. But even by seeing, you will not be able to distinguish which is convex and which is concave. Only by touch, only we will come to know which is convex and which is concave. In the case of convex lens, in the middle, that is thicker, at the edges, that is thinner. In the case of concave lens, in the middle, that is thinner, and at the edges, that is thicker, like that. Understood? Okay, now this is primary surface, that is secondary surface. Now, a light ray is incident as per the universal sign convention, from left to right. Now, this becomes the point of incidence. This is the tangent drawn to this. Got it? Now, perpendicular, which is normal, you need to imagine. As the light ray enters from air into the glass, the refracted ray will be moving towards the normal. The light ray will be just moving like this. This is the way how the light ray moves. Got it? Now, the second refraction begins. During the second refraction, this becomes the point of incidence. You need to draw one partner, there's a tangent over here for the sake of normal. Perpendicular to this tangent you draw, then it becomes normal. Yes. As the light ray enters from glass into air, the refracted ray moves away from the normal, denser to rarer, away from the normal. This is normal, away from the normal. Yes. This is the way for the light ray passes ultimately. Similar thing can be taken even in the other light ray. What is that? One light ray will be just passing over here, and the final light ray will be coming over here like this. In this way, you send as many light rays as possible through the lens. We see that after refraction, all these light rays will be just moving away from each other. They will be diverging. This is what divergence means. This is what divergence means. So, a concave lens is a diverging lens. A convex lens is a converging lens. A convex lens is a converging lens. Come on, please make note of it. These two diagrams. Right. Okay. Now, in the case of these lenses, just like rules we will be discussing. Rule number one. Of course, I will not run. You know this. I will just tell orally. Rule number one. What is the rule number one? When the incident ray is parallel to the principal axis, the refracted ray will be just passing through the focus. Do all know this? Do all know this? When incident ray is parallel to the principal axis, the refracted ray will be just passing through the focus. This can be taken as rule number one. Rule number two, when the incident ray itself is passing through the focus, the refracted ray will be parallel to the principal axis. This can be taken as rule number two. Next, rule number three, when the light ray, which is incident ray, passes through the center of curvature. When the light ray passes through the center of curvature, then what happens? The refracted ray will be passing through the center of curvature on the other side. Same, we cannot say, same in the sense that it has to come back. But when the light ray, which is incident ray, passes through the center of curvature, the refracted ray will be passing through the other center of curvature, which is on the other side of the lens. Got it? Next one, when the light ray passes through the optic center, that particular light ray will not exhibit any deviation. Straight path, the light ray exhibits. Straight path, the light ray exhibits. These four can be taken as four rules. So by means of these four rules, we will be estimating the image position in the case of lenses. Even that image position you are very well aware of. I will just tell orally without drawing, because drawing it takes much time. So convex lens. How many cases do we come across in convex lenses? 6 cases. And if at all object is at infinity, where will the image get formed? The image is formed at the focus, which is real, inverted, and highly diminished. Which is real, inverted, and highly diminished. Highly diminished means the size of the image is just like a point-sized image. Got it? Next, when the object is beyond the center of curvature, then what happens? The light ray will be just formed. The image gets formed between the center of curvature and focus on the other side of the lens, which is real, inverted, and diminished. Not highly diminished, but diminished. When the object is at the center of curvature, where will the image get formed? At the same center of curvature, which is on the other side of the lens. When you place, in the case of convex lens, all primary ones are on the right sides. Okay, all secondary ones are on the left side. So if you place object at C2, image will get formed at C1. Understanding? Next, if you place object between the center of curvature and the focus, which is between C2 and F2, then what happens? Image gets formed beyond the center of curvature, which is C1. Beyond C1, image will get formed, which is real, inverted, and magnified. If you place object exactly at the focus, then image gets formed on the other side at infinity, which is highly magnified, real, and inverted. Highly magnified, real, and inverted. When you place object between the focus and the optic center, the image gets formed on the same side. Only in this case, the image gets formed on the same side, which is virtual, erect, and magnified. In fact, this is what we will be using as principle of simple microscope. Okay, so since this case is very, very important, you don't draw all the cases, just this last case you draw. I am not drawing, but you draw. Right? When the object is placed between the focus and the optic center, when the object is placed between the focus and the optic center, the image formation diagrammatically you have to show. I am not asking all the cases, only one case I have asked. Only one case I have asked. Between focus and optic center. Yes, over. Without draw. Look at this. I am drawing. Here, I have taken a convex lens over here. This is a convex lens. Right? You try to draw the lenses as thin as possible. Now, first of all, you need to mention all the things. What are they? One is the principal axis. This is principal axis. Now, central plane, you need to mention over here. So this is central plane. This is central plane. And this is the optic center, which is C. First, you mention all primary ones, next secondary ones. Primary focus will be here, F1. Primary center of curvature will be here, C1. Next, secondary focus will be here, that is F2. And secondary center of curvature will be here, that is C2. Right? Now, object has to be taken between the focus and optic center. So, this is what object is. Object which is AB, you take. Object which is AB. Right? Now, you need to take one light ray passing parallel to the principal axis. Usually, this light ray will be passing through the focus on the other side. This is the way how the light ray passes. This is the way how the light ray passes. One more light ray you will be taking that passes through the optic center like this. This is the second light ray. And we see that these two light rays don't meet over here. These two light rays keep getting diverged as they pass to infinity. So, this side, there will be no image formation. Now, if at all observer sees from this side, for the observer, this light ray seems to be coming from the imaginary point. Even this light ray seems to be coming from the imaginary point. These two light rays will be just meeting over here. So here the image of the object will be formed. This is the image which is A dash and B dash. This is the image that is A dash and B dash. What kind of image is it? That is virtual image, magnified image. Virtual image and magnified image. This is the ray diagram for this situation. For this situation, that is the ray diagram. Got it? Now coming to the second category of lenses, that is a concave lens. In the case of concave lens, what kind of image formation takes place? This is what we need to discuss now. Just like convex lens, we don't come across all these cases. In the case of concave lens, only two cases we will have. One is when the object is at infinity. The second one is when the object is at a finite distance. When the object is at infinity, what happens? The image gets formed, yet the focus, which is virtual, erect, and highly diminished. Highly diminished. Got it? Okay. When the object is taken at a finite distance, then the image gets formed between the focus and the optic center, which is virtual, erect, and diminished. But now in this case, one more theoretical applicative question we can discuss. What is that? How will the image move as the object is moved towards the lens? Towards the lens, the object is moved. Then how will the image move? Towards the optic center, the image moves, not towards focus. When the object is moved away from the lens, then the image will be moving towards the focus. When the object is moved towards the lens, the image moves towards the optic center. You need to understand the movement of image with respect to the movement of object. You need to understand the movement of image with respect to the movement of object in the case of lenses, in the case of mirrors. Got it? Okay. So one case I will be showing over here, even for concave lens. Okay, I understand that there are some cases which are confusing in this regard. Okay, so this here you see concave lens image formation. So concave lens I am just showing over here. This is the concave lens. This is the concave lens. Even in this concave lens, you need to show all these things. The very first one is the principal axis. Next, the central plane needs to be shown over here like this. This is central plane. In the case of concave lens, all primary ones lie on the left side or right side? Left side. Okay. Now this becomes a primary focus over here. This becomes a primary center of curvature. Next, secondary focus will be here, F2, and secondary center of curvature here, that is C2. You need to place the object at infinity. You need to place the object at a finite distance. Only two cases are there. Second case I will take. Right? So second case, the object is placed beyond the center of curvature over here like this. This is the object over here, AB. Then what happens? The light ray will be just passing over here. And the light ray undergoes refraction like this. Divergence. This light ray seems to be coming from the focus. This light ray seems to be coming from the focus. And one more light ray, you need to take that passes through the optic center you take. Okay, so otherwise, one more light ray that passes through this focus you take. Anywhere you can take. Anywhere you can take. Okay, so this I will be just taking over here. So this is center of so optic center. So this light ray and this virtual light ray, both the things will intersect over here. So this becomes an image formation, that is A dash, B dash. A dash, B dash. Image gets formed on the same side, which is virtual, diminished, and erect. Like this. This is the image formation in the case of the concave lens. Concave lens. And the next concept of this lens is lens maker's formula. Lens maker's formula. lens maker's formula. Okay, lens maker's formula. What do you mean by lens maker's formula? Lens maker's formula is nothing but that is a formula which is to be applied while making the lens. That is a formula which is to be applied while making the lens. That is called lens maker's formula. That is called lens maker's formula. Usually, this lens maker's formula gives the relation between the focal length of the lens and the radii of curvatures R1 and R2. Radii of curvatures R1 and R2. And the refractive index of that particular material of the lens. And for this, there was a big derivation of the things that derivation that and all we need not read now. Lens maker's formula is 1 by f is equal to refractive index of this glass means the material of the lens. Refractive index of the material of the lens with respect to the medium in which lens is placed. And if I take glass lens, if I place that particular lens in air medium, then it becomes a refractive index of glass with respect to air. Refractive index of glass with respect to air -1. So this is what. Okay, so mu g a -1 into 1 by R1 minus 1 by R2. So this is what lens maker's formula. This is what lens maker's formula. By means of this lens maker's formula, you can calculate the focal length when all the terms of RHS are known. You can calculate the radii of curvatures. Anything you can calculate when the remaining things are given. When the remaining things are given. Got it? So by means of this lens maker's formula, you can obtain the relation between the focal length and the radius of curvature. The radius of curvature. What happened, Abhishek? Wake the fellow up. Hello. What, man? Dirty habit. Use this one. Stand up. Be like this for some time. Huh? This is a class which is very important in the so in terms of CET we have been discussing, and now you are sleeping. Huh? Okay, what does it mean? Highly irresponsible nature, irresponsible attitude. Huh? If at all you don't have any interest towards CET, just go home, man. Huh? Are you here to disturb others? Or if at all your health is not good, okay, so you need to take permission from principal and you have to go to hospital and you have to sleep. Huh? For everything there is, so there must be one way, there must be some solution. Very bad. And if at all you are not that much keen towards the CET, CET that and all are not required for me. Huh? The moment the result comes, okay, I will be joining somewhere in BS or in a degree or some outside work I will be looking at for yawning purpose. So if you think like that, you are not supposed to be here. With this type of unwilling nature, what happens? The remaining people will get affected. Even if any boy is very much interested in learning that, the fellow is very casual like that. We also could be. Unnecessary thoughts will get cultivated in the minds of remaining people. You can spoil yourself, but you should not spoil others. You don't have right. Okay, so here, this is the lens maker's formula. Now, what I do is, I will be just taking one lens of here. This is the lens of here. This is the lens. Sit down. Sit. So, this is the lens. Right? Now, in this particular lens, what I do is, I will be taking the two radii of curvatures same. Two radii of curvatures same. So, radius of curvature, primary radius of curvature will be in this direction. So, that is R1. The secondary radius of curvature will be in this direction. So, that is R2. Right? So, these two radii of curvatures equal I will take for convenience of discussion. So, R1 is equal to R2 is equal to R. Same. Right? The refractive index of this particular lens is mu you take. Right? and the focal length of this particular lens is small if you take. If at all you apply this lens maker's formula for this data, 1 by f in this particular case is equal to mu minus 1 into. For this radii of curvatures, you need to apply the sign convention. For the radii of curvatures, you need to apply the sign convention. R1 is on the right side. Right side in the sense of positive, it becomes. R2 is on the left side. Left side means negative, it becomes. Whatever the values that you are going to take with the sign convention, you need to substitute the values. With the sign convention, you need to substitute the values. Got it? Okay. So 1 by R1. 1 by R1 means 1 by R. Which R plus R? Minus. 1 by R2. R2 means which R minus R. Here 1 by F in this particular case is equal to mu minus 1 into. This is 1 by R plus 1 by R. 1 by R plus 1 by R. Got it? This is 1 by F is equal to, this is mu minus 1 into 2 by R. By cross multiplication, what do we get? What do we get? So this is R by 2 is equal to F into mu minus 1. Am I correct? Therefore, F is equal to R by 2. F is equal to R by 2 for mirror. Now, mu minus 1 for lens. But F is equal to R by 2 alone, if it are there. That is applicable for mirror. Now, F is equal to R by 2 into mu minus 1. F is equal to R by 2 into mu minus 1. That is for lens. This is the relation between the focal length and radius of curvature in the case of a lens. In the case of a lens. Yes, over. Now, the next formula that you need to keep in mind in this regard is lens formula. Lens formula, we need to take lens formula. Lens formula. So, what do you mean by lens formula? This is what we have to think of now. Usually, this lens formula establishes the relation among the object distance v and the image distance v. Okay, object distance u and image distance v and focal length, that is. The lens formula says that 1 by f is equal to 1 by v minus 1 by u. So this is what lens formula. 1 by f is equal to 1 by v minus 1 by u. 1 by f is equal to 1 by v minus 1 by u. This is lens formula. This is lens formula. Got it? Now, in this regard, one more formula we have to keep in mind, that is magnification. Formula for magnification. Formula for magnification. So, what is magnification formula? Magnification m is equal to plus v by u, or magnification m is equal to hi by hu. In the case of mirror, the magnification is minus v by u, whereas in the case of lens, magnification is equal to plus v by u. Magnification is equal to plus v by u. Plus v by u. Got it? So these are the formulae. And one more thing, one more important formula we come across in the case of lenses. Sometimes lenses are taken as a combination. When the lenses are taken as combination, then what happens? Focal length will get affected. whatever the focal length that we write for a single convex lens, that single focal length we don't come across. So whatever the two lenses that we are taking in the combination, each lens will be having its own focal length separately. But when you take those two lenses as a combination, the focal length becomes effective, which is called effective focal length or total focal length, whatever it may be. Now, the type of combination can be taken in two ways. Look at this. The two lenses are taken as a combination in which they touch each other. See, this is one lens, and one more lens I will be just taking like this. In optical instruments, we will be using this type of combinations, usually. Now, the first lens focal length f1 you take, and the focal length of the second lens, that is f2, you say. Right? Now, the combination effective focal length, the combined focal length is nothing but 1 by f1 plus 1 by f2. So this is the formula that we have to keep in mind while solving the problems. But one more thing we need to keep in mind, that always these two lenses need not be taken together, means in contact. There can be some gap between the two lenses. When the lenses are taken at some gap from each other, then how do you write the equation for effective focal length of such combination? Look at this. This is that situation I am talking about. So this is one lens I am taking, and one more lens I am taking over here. This is the other lens. Let this be the focal length of the first lens. Let this be the focal length of the second lens. There is some distance between the two lenses. Let that distance be x. Let that distance be x. Now, the total focal length is equal to, or effective focal length, or combined focal length. How do you write? So this is f1 minus 1 by f2 minus, okay, x by f1 plus f2. This is a combination of plus and plus. Minus comes with respect to sign convention. Sign convention in the sense, if you take a convex lens, look at this. Primary ones only we take. For a convex lens, primary focus lies on the right side. Remember. Therefore, focal length is positive for a convex lens. For a convex lens, the primary focus is on the right side. Therefore, the focal length in the case of a convex lens becomes positive. Next, for a concave lens, look at this concave lens I am taking. Right? And here, the primary focus lies on the left side. So primary focus will be here. Primary focus will be here. So this focal length we need to take. So this is negative. So in the case of concave lens, the focus becomes negative. Whenever you do any problem by using this concave lens, focal length has to be taken as negative, because the primary focus lies on the left side. The primary focus lies on the left side.
Yeah, 1 plus f2
f1 into f2. This is f1 into f2. f1 into f2. 1 by f1 plus 1 by f2 minus
1 by f1 plus 1 by f2
minus. This is minus. 1 by f1 plus 1 by f2 minus x by f1 into f2 minus x by f1 into f2. Okay, so while using these two formulae, we need to apply sign convention. Okay, whenever we come across a concave lens, there we have to go for negative. Whenever we use a convex lens, there we have to go for positive. Got it like this. So this is something about the last concept, okay, after which we can take up the problems. Power of a lens. Power of a lens. Power of a lens. What do you mean by power of a lens? It is symbolically represented by P. The symbolic representation is P over here. Power of a lens. Right? Okay, so power of a lens is nothing but reciprocal of focal length. Usually, while handling with this, while dealing with this power, this focal length has to be treated in terms of meter. Usually, while using lens maker's formula, this focal length you can keep it as a centimeter. But when it comes to power of a lens, focal length has to be converted into meter. That is the rule. Right? So per meter becomes the SI unit of this power. So per meter in the SI system is defined as 1 diopter. 1 diopter. Okay, the symbol is 1 capital D. The symbol is capital D. Got it? So same power concept we will be applying even for the combination. When the lenses are kept in contact with each other, the effective focal length 1 by f is equal to 1 by f1 plus 1 by f2. Therefore, the effective power P is equal to P1 plus P2. When the lenses are kept at some separation, then the effective focal length is 1 by f is equal to 1 by f1 plus 1 by f2 minus x by f1 into f2. So, in terms of power, if at all we want to write P1 plus P2 minus x into P1 P2. X into P1 into P2. P1 into P2. Right? Oh, okay. So, the lenses, all concepts are over. So, next optical instruments, small topic. So, that I will discuss in the evening along with the problems we have discussed. Now, the class is still complete. Now, probably 8 only. Right? Now, probably this you have received that worksheet. Huh? So, one of the worksheets you please give it to me. I don't have paper. Do you have paper here? Huh? So, that paper you adjust, both of you. Yes. Now, please open this paper. You adjust this with the Maheshwari for some time. After the class is over, you get the paper from office. Okay? Yes. Now, look at the first question. Look at the first question. A man 2 meter tall stands in front of a vertical plane mirror. What is the minimum height of the mirror and how high must its lower edge? Okay, be above, that's B. Be above the floor if he is to be able to see his whole body. Assume his eyes are 10 centimeters below the top of his head. Okay, so there's in this particular case, of course, options I did not mention. There's each and everything that you have to work out. But okay, now there's here you see this. Let me explain. In this question, there are 2 things involved. In this problem, there are 2 things we have to work out. In this problem, there are 2 things you need to work out. Look at this here. A man 2 meter tall stands in front of a vertical plane mirror. And first of all, you need to have the general idea. If at all a person stands in front of a plane mirror, what should be the minimum size of the plane mirror so that the person will be able to see the complete image? How much? Half of. Okay, half. So this here, for everything, there's a reason you have to know. Got it? So look at this here, you see, I am explaining. So look at this here, you see. This is man. Okay, this is man. Look at this. This is the top of the man. This is the feet of the man. Got it? So the man has to get his image ultimately. The image formation of the things takes place by means of his eyes. So you need to look at the eyes position also. Let eyes be here. The eye of the man, okay, is here. Got it? Okay. Now, so this here there is a wall. Now, in front of this wall, there's a here in front of the man on the wall. There is a mirror kept up here like this. This is the mirror that is M here. This is the mirror that is M and N. Right? Now, the minimum size of the mirror so that the person has to see the complete image of him in the mirror. So this is what the question is. This is what the question is. Right? See here, if at all the person wants to see, okay, so his top, so the light ray has to pass like this, the light ray has to touch the mirror M, that is extreme top end. The light ray has to undergo, okay, reflection. The light ray has to reach, okay, the eye of the observer. So this is the eye of the observer you take. This is the eye of the observer, eye of the observer. Right? This is the eye of the observer, you say. Right? So here it is. So this is the way how the light ray, reflected ray, so light ray moves. Understand? Now, during this refraction, normal drawn through this point of incidence, that's if you draw like this, so this becomes normal over here. This becomes normal over here. Since it is a regular reflection, so this becomes the angle of incidence, this becomes the angle of reflection. In the regular reflection, the angle of incidence, the angle of reflection, both the things are same. When both the things are same, so these two things will be same. And if at all you take this A to E distance as x, then it becomes x by 2, this becomes x by 2. So the distance between A to E, that is x, I have said. The distance between the eye to the feet of the observer, so y, you say, this is y. And if at all the observer wants to see his feet, okay, so the light rays have to travel like this, from B. From B, the light rays have to travel like this. Even this light ray has to undergo reflection. After reflection, this light ray will be just reaching the eye of the observer. This is the way how the reflected ray moves. This is the way how the reflected ray moves. Got it? Now again, if at all you draw normal, which is perpendicular to this wall, that is to the mirror through the point of incidence, what happens? This becomes the angle of incidence, this becomes the angle of reflection. Again, since it is a reflection by plane mirror, this reflection is a regular one, in which the angle of incidence is equal to the angle of reflection. Of course, in my drawing, both the things, okay, are not. Okay, so looking like equal, but imagine both the things are same. When these two things are same, actually these two things also be the same. Yes or no? So this becomes y by 2, this becomes y by 2. And the total height of the person, h you see. Then this h is equal to how much? X plus y. H is equal to x plus y. Now, if you see carefully, so this is m, n, and whatever the normal that you have drawn here, so this is A, B, and E. Okay, m, n. So this is C, and this is D, C. Now, what do you say about C, M, N, D, C, M, and D? It's a rectangle. It's a rectangle. In this rectangle, the opposite sides are equal and parallel. That is equal to CD. So MN is equal to CD can be written as CE plus ED. Can we write like this? MN is equal to CE is nothing but x by 2. ED is nothing but y by 2. That is MN is equal to x plus y by 2, so which is nothing but h by 2. Which is nothing but h by 2. But by means of this discussion, what can you conclude? If at all you want to get the full image of the person with the mirror, the size of the mirror has to be half of the size of the person. Half of the size of the man. Right? In that way, now in this problem, what is given? The height of the man is 2 meters tall. Okay, so what should be the minimum size of the mirror that is required to see his complete image, to see his full image? 1 meter. That has to be 1 meter. Right? Half of that. Okay. Okay. So please draw this. And one more question we need to answer over here. And what is that? What is the minimum height of the mirror? Okay, answer. And how high must its lower edge be above the floor if he is to be able to see his whole body? Lower edge. This is the lower edge. Okay. So this height you need to calculate. This height you need to calculate. Got it? So this is n and this is n dash. You take n dash is equal to how much? This is what we need to calculate. Got it? See here. First, this you have this. Yes, over. Now the second part of question we will look at. See, and how high must its lower edge be above the floor if he is to be able to see his whole body? Assume that his eyes are 10 centimeters below the top of his head. So look at this. This is the top of his head, and eyes are 10 centimeters below. So AE is equal to 10 centimeters. AE is equal to 10 centimeters. AE is equal to 10 centimeters. Got it? Yes or no? Mn is equal to 1 meter. Mn is equal to 1 meter. That implies. So this is here. CD. Am I correct? CD. CD is also equal to 1 meter. 1 meter. Understood? So from here to here 10 centimeter, from here to here 5 centimeter. 5 centimeter. Got it? Okay. So AC is equal to 5 centimeter. 5 centimeter means 0.05 meter. Right? Now, so AC is 0.5, CD is 1 meter. So what is AD? What is AD? AD is equal to how much? 1.05 meter. 1 plus 0.5 meter. 1.05 meter. Understood? Now, so how high means there is n dash. N dash, that is nothing but dB. Am I correct? N dash is equal to dB. Yes or no? So dB. So here, the total height is how much? 1.05. Got it? So how much? So 2.00, 1.05. Okay. So this is 0.95 meter. 95 centimeter. 0.95 meter, which is nothing but 95 centimeters. 95 centimeters. But the lower edge of the mirror has to be at a height 95 centimeter from the ground so that he will be able to see the full image. Okay? Right. Now coming to the next second problem. A 2 centimeter tall object is placed 15 centimeter from a concave mirror of focal length 10 centimeter. Find the position, size, and the nature of image. Okay, so we will come across many such kind of problems. Just one or two problems. I will explain the main problems you can. Okay. Come on, please make it faster. Yes, started. Right. On this mirror formula and magnification aspect, if at all anyone is new, just listen to the board. Listen to me. Okay, look at the board. A 2 centimeter tall object. Height of the object has been given. Usually, height of the object is always above the principal axis. That will be positive. Okay, is placed 15 centimeter from a concave mirror. So this is a concave mirror. You write like this. So that what happens? Okay, for that particular mirror, should the focal length be taken as positive or negative, there will be some clarity in your mind. But so concave mirror has been given. Now 15 centimeter is the distance, object distance, minus 15 centimeter. Why minus? Always object distance has to be negative because object is always taken on the left side, because universal sign convention says that propagation of light ray has to be from left to right always. Left to right always. But in that way, so object will always be present on the left side of the pole or optic center in the case of lens, like this. Got it? So negative we have to take. Coming to focal length. Focal length. So for concave mirror, look at this. This is the concave mirror. This is the concave mirror. Now this is the principal axis and this is the pole over here. So this is the focus. Focal length has to be measured from pole. In the left direction you are measuring. Since you are measuring the focal length in the left direction, so for concave mirror, focal length becomes negative. Focal length becomes negative in the case of concave mirror. In the case of concave mirror, so this becomes minus 10 centimeter. Find the position, size, and the nature of image. Okay, position of the image B is equal to how much? So it's the nature of image you need to discuss, and the size of image also you need to discuss. These are the things that are to be done. Okay. Now from mirror formula, what do you say? 1 by F is equal to 1 by B plus 1 by U. Substitute with the sign convention. F is minus 10. So minus 1 by 10 is equal to 1 by B minus 1 by 15 because the U value is negative. So 1 by V is equal to 1 by 15 minus 1 by 10. So take the LCM like this, 15 into 10. 15 into 10. But 10 minus 15. So 1 by V is equal to minus 5 by 15 into 10. This 3 times. Therefore, V is equal to minus 30 centimeter. V is equal to minus 30 centimeter. So at a distance of 30 centimeter, the image gets formed. The image gets formed. Okay, so by means of this minus 30, what do we know? On the left side only, that's all. So if that is a real, virtual, that information is not there so far. V is equal to minus 30 centimeter means by means of this, what can we tell? By means of this value, image is at a distance of 30 centimeter, which is on the left side. That's all. Now, for nature of image magnification, we have to calculate. Okay, for nature, okay, so magnification of mirror is to be found. Magnification is to be found out. Magnification is to be found out. Is to be found out. Magnification is to be found out. But okay, so for nature, magnification m is equal to minus b by u. Magnification m is equal to minus b by u. So magnification negative. So b value how much? Minus 30 you got, and u value how much? Minus 50 you got. So magnification m is equal to minus 2. Now complete information has come. Magnification is negative, means real inverted. Finish. Magnification is equal to 2, which is more than 1, magnified. So image is real, inverted, and magnified. Image is real, inverted, and magnified. Okay, now the size of the image we need to calculate. We know that magnification is equal to h. Magnification minus 2, you make minus 2 is equal to hi by ho. What is the size of the image? 2. Therefore, hi is equal to minus 4 centimeter. See, even in the size of the image, negative sign has come. Negative sign has come. So that negative sign shows that image is inverted. Why minus? Because it is below the principal axis. It is below the principal axis. When it is above the principal axis, positive. When it is below the principal axis, negative sign convention. But this is the way how we have to work out the problem. Come on, please note it. Next problem. The image of an object in a convex mirror is 4 centimeter from the mirror. If the mirror has a radius of curvature 24 centimeter, find the position and the magnification. Just like the previous problem, I hope you can do. Okay? Do it. Now I am not doing, but do it. You do it. That is it. That is third one. That's we didn't read it. Okay, third one. An object is placed 10 centimeter in front of a concave mirror. Object distance is minus 10. Of focal length 15 centimeter. Focal length of a concave mirror is negative, minus 15. Find the image position. V is equal to how much? And magnification m is equal to minus v by u. M is equal to minus v by u. So this you can do by using the method of second problem. Next, fourth problem also we can do. Okay, next, fifth problem. An erect image 3 times the size of the object is obtained with a concave mirror of radius of curvature 36 centimeter. What is the position of the object? What is the position of the object? Okay, so this I will work out because this is very easy, but data is given in a different way. Data is given in different manner. Okay, so look at this. The problem is here an object. There's an erect image. Erect image. Look at this. Here, erect image is formed. That means what is this? Virtual. This is virtual image. Erect image means that is virtual image. That is virtual image. Got it? Okay. So 3 times the size of the object. So hi is equal to 3h2. By means of this magnification becomes what? For a virtual image, magnification is possible. Right? So plus 3 h2 by h2. Because of magnification formula, hi by h2. So magnification plus 3h2 by h2. Therefore, magnification is equal to plus 3. Magnification is plus 3. Understood? Okay. So a concave mirror, the given mirror is concave. The given mirror is concave. Radius of curvature has been given 36 centimeter. Radius of curvature has been given 36 centimeter. For a concave mirror, radius of curvature becomes negative. That implies focal length is minus 18 centimeter because focal length is equal to r by 2. In the case of mirror, focal length is equal to r by 2. Minus 36 by 2 minus 18 centimeter. What is the position of the object? V is equal to how much? Okay. So by mirror formula, that is 1 by V plus 1 by U. 1 by F minus 1 by 18 is equal to 1 by V. Minus, but here you see, V, that's the U value is not given. U value is not given. So for that purpose, what I do is magnification is equal to minus V by U. Got it? Magnification is equal to minus V by U. So what is magnification? Plus 3 minus V by U. Okay. So that implies V is equal to plus 3. Since we need to find out V in terms of V value, that's it.
Object. Object.
We need to calculate position of object. So you will be able to find out. Okay, so V is equal to minus 3. V is equal to minus 3. Got it? So by mirror formula, 1 by F is equal to 1 by V plus 1 by U. Got it? Minus 1 by 18 is equal to minus 1 by 3U plus 1 by U. Understood? So minus 1 by 18 is equal to, this is 3U into U is a LCM, minus U plus 3U. Okay, so minus 1 by 18 is equal to 2U by 3U into U. U will get cancelled. Understood? By cross multiplication. And before that, this can be cancelled 6 times. Okay, so therefore, U is equal to minus 12 centimeter. U is equal to minus 12 centimeter. U is equal to minus 12 centimeter. Right. Next problem. A convex mirror of radius of curvature 20 centimeter forms an image which is half the size of the object. Look at the position of object and its image. Both V and U, you need to find it. Both V and U, you need to find it. Same model. And in this U value we found out, wherever this U value you substitute here. V value will come. V value will come. Okay, so now the time is 12:45. So, okay, it's more than one of the others. So it was like, okay, 10:30 we started now. Okay, so now we will wait up the class. Okay, when you will take the paper, you stop this. Afternoon wave optics. Afternoon wave optics. Got it?